Hey guys, so I'm going to do this through YouTube. I think YouTube is going to be the easiest way for me to deliver content to you guys. So I'm going to try and upload all of the stuff that we haven't covered yet. But if you do want to go back over something or you want me to do a worked example, then just send me through an email and then I can go through and do a worked example for everybody. And then I'll upload that to my YouTube channel, and I'll have a specific playlist for you guys. So this first topic, I know that we've covered this before, but I had a few questions about this today. But how do we do proof by induction? Because I haven't got any of the written examples up there for you. So let's just go through a quick little refresh, right? So proof by induction. Induction, right? It's this weird sort of idea, and I always think of it as like the domino effect, right? For lack of a better term. So if I was to knock over this first domino, okay, so in other words, if I was to, this is the first domino, n is equal to 1. If I was to knock over this first domino, I'm going to assume that this is going to knock over the second domino. And if it knocks over the second domino, I'm assuming it's going to knock over the third domino. And if it knocks over the third domino, it should knock over the fourth domino, and so on and so forth. So what we really are doing when it comes to testing things through induction is if I come along and I check this domino here, and I assume that this domino has been knocked over, and this is just any random number of dominoes. If I have a look at the domino after that, and that's been knocked down as well, then that means that all the dominoes have probably fallen. So this is the whole reasoning or the whole idea behind proof by induction. So we test the first domino and we see if that's fallen. We assume that this domino has fallen, and then we check to see if the following domino has fallen. And assuming that that has all happened, that means that all the dominoes will have fallen, or the mathematical statement is true through induction. Okay, so this question here, I'm not going to go through the questions that the textbook wants us to answer. I just want to show you that the process of proof by induction. Okay, so for this one, 2 plus 4 plus 6 plus blah, 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 all the way up to 2n. Okay, should be equal to n times by n plus 1, as long as n is greater than or equal to 1. Now in this case, because n is greater than or equal to 1, our first case is going to be when n is equal to 1. If we had n greater than 1, then I would pick the next value after that. So I would say n is equal to 2 for the first case, right? But for this one, we're going to just use n is equal to 1. So I'm just going to substitute my values in. Now for this one, what it's saying is I'm summing up every even number until I get to 2 times by the number that I'm interested in. So basically for this first one, I'm only substituting in one value, n, which is 1. So I have 2 on my left-hand side. For my right-hand side, I'm going to substitute in those values. So n is equal to 1 times by 1 plus 1. And we know that is going to be true because my left-hand side is equal to my right-hand side, and so therefore I've proven that the first case is true. Now what I'm going to do is I'm going to assume that the kth case is true. So I'm going to assume that this is true. I don't actually know for certain, I'm assuming. So if I substitute this value in for k now, I don't know what the number k is, so I'm just going to write 2 plus 4 plus 6 plus ... all the way up to 2k, whatever that happens to be. And that should be equal to k plus 1. Okay, so I'm assuming that this is going to be true. Now what I'm going to do is I'm going to use this information to help me answer the final statement, or to test the final statement. And that is testing the next domino, so testing k plus 1. So effectively, I'm just going to substitute in this value into here. So I've got 2 plus 4 plus 6 plus ... plus 2k. So that would have been this previous case here, plus 2k plus 1, okay? And that's going to be equal to, if I substitute k plus 1 into here, k plus 1. So I'm substituting it in for n, and I'm going to substitute it in for this n, k plus 1, plus 1. All right, so effectively what I've done is if I say all of this is equal to this, then what I'm going to do is I'm going to replace all of this with this piece of information here. So I now have k plus 1, plus 2, k plus 1, and that should be equal to this right-hand side here. I'm going to simplify this, so this is going to be k plus 1, k plus 2. Okay, and now I'm just going to show that the left-hand side is equal to the right-hand side. So I'm going to do that by expanding the brackets and then collecting the like terms. So first of all, I've got k squared plus k plus 2k plus 2, and that should be equal to k squared plus 2k plus k plus 2. All right, let's collect our like terms now. So I'm just going to collect them on the left and the right-hand side. I'm not going to move anything across the equal sign. So I have k squared plus 3k plus 2 should be equal to k squared plus, 3k plus 2. So for this one, the left-hand side is equal to the right-hand side. So that's proven to be true. Okay, so I've shown that this first case is true. I've assumed that the second case is true. And because I'm assuming that this case is true, I'm going to use that information, substitute it in here. So doing a little bit of algebra, and then I've shown that this case is now true. So because I've done 1, 2, 3 things, therefore the statement is true by proof of induction. So that's the inductive method. All right, we can have another go here. So question 2, so consider the statement, the sum of all the numbers from 1 to n, where of the function 2 to the power of r minus 1 should be equal to 2 to the power of n minus 1. So effectively what this information here is stating, if I did the first one is going to be 2 to the power of 1 minus 1 plus 2 to the power of 2 minus 1 plus 2 to the power of 3 minus 1, and so on and so forth until I get to 2 to the power of r minus 1. So whatever this value r ends up being, right? And that's going to be equal to 2 to the power of n take 1. Okay, so I'll show you how this works. If I have 2 to the power of 1 take 1, that's going to be 0 plus 2 plus 4 plus 8 plus ... all the way to 2 to the power of n take 1 should be equal to 2 to the power of n take 1. So that's all that this sum of notation means. Okay, so again, I'm not going to answer these actual questions from the textbook. I'm just going to use that information to show you proof of the inductive method. So going back, we're going to prove that the first case is true. Now, does this have a restriction on n? Okay, so the only restriction here is this one. So the first case is when n is equal to 1, which is good. That's what I've written. So let's substitute those values in. So all I'm going to be saying is the sum of all the numbers. Oh, well, this first one is just going to be 2 to the power of 1 take 1, which is 2 to the power of 0, which is 1. And that should be equal to 2 to the power of 1 take 1. 2 to the power of 1 is 2, 2 take 1 is 1. Left-hand side is equal to the right-hand side. So therefore, the statement is true for the first case. Now we're going to assume that it's true for this case here. So all we're really going to do is just substitute in some values. So I'm just going to substitute everywhere that I see a k, I'm going to substitute in, everywhere I see an n, I'm going to substitute in a k. So I don't feel like writing out all this information, that's why I'm using the sum of. So I'm going from 1 to k, summing all the values from 2 to k, take 1. And that should be equal to 2 to the power of k, take 1. So I'm going to assume that this is true. All right, so now what I'm going to do is I'm going to have to give myself some more space here, 1 second. Okay, so now what I'm going to do is I'm going to take this information and I'm going to use this information to help me prove that it's going to be true for the following case. So effectively what I'm going to do, if I was to add all of the cases from 1 to k for the sum 2k take 1, then I already know that's equal to 2k take away 1. All right, so now what I'm going to do is I'm going to substitute in the value of k plus 1 instead of this previous case. So I'm going to have the sum of 1 to the power of k to k take 1 plus 2 to the power of k. This is getting a little bit confusing here, I know, but effectively what I've done is I've said I'm going to take this and I'm adding the next term. Right, so that's all I've done. I've taken this previous term and I've added the next term, and that should be equal to 2k plus 1 take 1. Okay, so now I need to prove that to be true. So effectively what I'm going to do, because I've just substituted this value in here, this is also going to be equivalent to that. So I can substitute that in there. So 2 to the power of k take 1 plus 2 to the power of k should be equal to 2 to the power of k plus 1, take away 1. So what I'm going to do is I'm going to factorize these. So I have 2 to the power of k, 1 plus 1, take 1. And then that's going to be equal to 2 to the power of k plus 1 minus 1. Now this is going to be 2 to the power of k times by 2, take 1. And that's going to be equal to this. Oh, I've got to scroll down. Sorry, one sec. Okay. Now, if I have 2 to the power of k times by 2, remember when we're multiplying things with the same base, we add their index. So in this case, the index is k. In this case, the index is 1. So it's going to be 2 to the power of k plus 1 minus 1 is equal to 2 to the power of k plus 1 minus 1. So the left-hand side is equal to the right-hand side, and therefore this statement is true by induction. I don't feel like writing that all out, but this is just going to be proof of induction. Okay, so this one was a little bit more confusing than the last one, but I hope that I kind of explained that well. Effectively, all we're doing, it really just comes down to algebra skills. So you really just have to be very, very confident with those algebra skills because we're doing a lot of substitution, okay? If you want me to go over this in a little bit more detail, I will do that for you now. So just to sort of go over and explain that. Effectively, what this is saying is I'm adding 0 plus 2, plus 2 plus 4 plus dot, 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 all the way up to 2k take 1. And then the next term is going to be this plus 1, so it's going to be 2 to the power of k. So that's where that came from. So effectively, this represents this little bit here. This represents this bit up here. So I kind of hope that explains it a little bit better. Anyway, so that's proof by induction. So if you want, I can go through some more videos for you. Just let me know. Just comment on this video, you know, if you want me to go through a few more of those textbook questions for you. Otherwise, I'm going to assume that we're all doing okay. Fingers crossed. All right, I'll talk to you guys soon. Bye.